In Precalculus, section 2.5a, we're dealing with rational functions. Now in section 2.5, we're going to split it into two sections. A rational function is a quotient of two polynomial functions. So we've dealt with polynomial functions before, and when we put them in a quotient, so a division, we get a rational function. Now, the key is that just like with any other fraction, if the denominator is 0, it's undefined. So the denominator of this rational function cannot equal 0. And we're dealing with something called asymptotes. And asymptotes are lines where the graph of the rational function are undefined. This will help us figure out how to graph the rational function. And again, there's certain places where they are undefined. So the first step, find the domain of each. So the first question says to find the domain of each function and the equation of the vertical or horizontal asymptote. So we're going to break this down. We're going to first identify the domain. Now the domain, if you remember, is what we plug in for x. It's all our x values. Now we can plug in any number into this equation except the domain cannot, the x that we cannot use is what makes the denominator 0. So when we figure out the domain, we just set this denominator right here and we set it equal to 0. X minus 1 equals 0. And when we solve it, we get x equals 1. So that means if I plug in x equals 1, it'll give me a 0 for the denominator, making it undefined. So this then, x in the domain, x can be anything except x cannot equal 1. The horizontal asymptote here is just anywhere the domain is not defined. So the horizontal is a place in the graph that has a vertical line where the graph cannot go because it makes the equation undefined. So there's a horizontal asymptote at x equals 1. So it should be 1 positive right there. There should be no, the graph there should be no points for that graph. Right? So let me show you. When I graph this, the x over x minus 1, if you see there, and I graph it, it looks like this, right? So you can see that at x equals 1 right here, there's this vertical asymptote. That means it, and when I hit the table and I go to -1, or sorry, +1. Sorry about this. It's error because it's undefined. Now, the vertical asymptotes are a little bit more difficult because we're not looking for an error sign, we're looking at the behavior of the y. So if I go down to all the positives and I hit, and I go as far as I can, it'll decrease and it'll keep decreasing to 1, but it'll never actually hit 1. And in this case, the opposite direction, I'm following that behavior as well, and I'm looking at the pattern. It'll increase to get close to 1, but as you can see, it'll also never hit 1. So if I'm looking at the table here, if I'm looking at the graph here, at +1, y equals +1, there's also there's a horizontal asymptote. Oh, I apologize. The vertical asymptote is x equals 1, and the horizontal asymptote is y equals 1. So it's undefined at 1 here, and it's undefined at +1 here. You can see that the graphs curve around those asymptotes. So it's basically an invisible dashed line. And we'll be drawing those invisible lines to show work in your work. So go ahead and pause and write this down. So in this one, it asks us for graphs of rational functions. And we're going to attempt to now graph these functions using the information we know from the previous sections, and also the graphs of the rational functions. Now, you don't always have time, and it's not always as easy to analyze the table for your function. So, vertical asymptote is easy. You take the denominator, make it equal to 0, and that's where that's where it's undefined. The horizontal asymptote, on the other hand, is this situation right here. These are our three cases. N being the highest power of the numerator, and m being the highest power of the denominator. So if n is smaller than m, you have horizontal asymptote at 0. If these equal each other, then you have a horizontal asymptote at the coefficient over each other, so a sub n over b sub n. If n is bigger than m, there is no horizontal asymptote. That means there is no area where the y is undefined. The intercepts are basically when x equals, well, we've done intercepts before. It's when you put in 0 for the other variable. So x-intercept, you put in 0 for y. The y-intercept, you put 0 in for x. So these are important for us to know, to get an idea of where the graphs are going to be. So to graph a rational function, we have to simplify if possible, then find the domain, so we can figure out where the horizontal asymptote, the vertical asymptote is. Once we define the domain, then we figure out where the horizontal asymptote is, find and plot the intercepts, and then find and plot at least one point in the intervals determined by any x-intercepts and vertical asymptotes. So basically, we're going to then, using this information, plot in between so that we know how to graph. And that might be a lot. Go ahead and pause and write this down, because these instructions need to be near you so that we can figure out how to graph this. So, when we graph x squared minus 7x plus 10 and x minus 3, we're going to start with seeing if we can simplify. Now, two numbers when multiplied together gets me negative 7, but when added together it gets me positive 10. Negative 2 and negative 5 over x minus 3. So I can't cancel any of this out, so therefore I cannot simplify. So we move on to step 2. Find the domain. Now the domain is when the denominator x minus 3 equals 0 and x cannot equal 0. So that means the first asymptote, the horizontal asymptote, is x equals 0. So, sorry, the vertical is x equals 0. So right here, that means the graph is undefined at, 3. What am I thinking? Sorry. So x equals 3. The horizontal asymptote can be found by paying attention to the powers here. So our n is our top one, right? Yes, our n equals the power of 2, and our m is 1. So in this case, our n is bigger than our m. Our n right here is bigger than our m, and our bottom one. So therefore, this has no horizontal asymptote. Okay, our next step, we found and sketched the asymptote, then we have to find and plot the intercepts. So the first thing to do is to make this, so the y-intercept is when I put in 0 for x, so 0 squared minus 7 times 0 plus 10 over 0 minus 3 equals 10 over negative 3, which gives us 3.3, I believe. Yes. So this is negative 3.3. So around negative 3.3, we hit the y-intercept. Here's x, here's y. So negative 3.3. So it hits somewhere, not somewhere like 0.5. There it is. Okay? And then the x-intercept. The x-intercept, we plug in zero equals. And I'm going to do it for this one because I'm going to have to do this eventually. So x minus 2, x minus 5, x minus 3. So I'm going to go ahead and cross multiply, which then gives me 0 equals x minus 2 and x minus 5, which tells me that there's an intercept at x equals 2 and x equals 5. So at 2, there's a connection, and then at 5, there's a connection. So what you need to do here is then test each what you need to do then is just to test for each one to see how it approaches the asymptotes. So we have to then find points on these sides, or the last step is to find and plot at least one point in the intervals determined by x-intercepts and vertical asymptotes. So we have vertical asymptotes here, so we have 2 points on this side. So at least I know that this looks like this. But here I only have 1 point, and I don't know whether to go, it's going up or it's going down. So I'm going to test a point here. Usually you'll have to test more than just one, but in this case we lucked out, or I chose it on purpose so I didn't have to make this video longer. Whichever one you want to believe. But let's test 4. So if x equals k to 4, 4 squared minus 7 times 4 plus 10 over 4 minus 3. 4 squared is 16 minus 28 plus 10 over 1. 16 minus 28 plus 10 is negative 2 over 1, so which is the same thing as negative 2. So in this case, the point here is 4 comma negative 2. So 1, 2, 3, 4 comma negative 2. So it goes this way. So then that means it hits that way. And hopefully that's what the graph looks like. Let's just check. Plus 7x. plus 7x plus 10 parentheses divided by x minus 3. Graph. It was wrong for a second and I freaked out, but I had put plus 7 instead of minus 7. Whoop. So, as you can see, it looks like that. And if we zoom in, it should match what we have there. Which, let me zoom in. So we have that asymptote going up. Now if this kept going, you would see more of this, but that is what we graphed. So go ahead and pause and write this down. Now I have it here that I'm going to do another graph, but I think maybe you should try it on your own. There's just one more to the graph rational function that you can put on this list of horizontal asymptotes. These are called oblique asymptotes. Now we're not going to do the actual example, so I don't make this video longer. But when m is just one more greater than n, there's something called a slant asymptote. So it's an asymptote that's a line that's either this way or that way, so it's not just straight up and down or straight left and right. And in order to find it, you need to do ax divided by bx and find what the answer is. And if there's a remainder, it doesn't matter. Just focus on what the answer is without the remainder. So in this case, we would do x plus 3 divided by x squared minus x minus 8, right, to find the slant asymptote, because this is 2 and this is 1. So that means our m is one more bigger than our n is one more bigger than our n. So if I divide here, we have x plus 3. We put x here. So we have x times this x squared plus 3x. And I'm subtracting, so -1 minus -3 is -4x minus 8 gives me minus 4, which gives me -4x minus 12, right? And then there's minus positive 4. So remainder 4, but I'm focusing on just this. So y equals x minus 4. So I would do the same thing that I did in the last section, except in this case right here, right? If I start at -4 here, right? And I go up 1 over 1, up 1 over 1, up 1 over 1. There is an asymptote, a slant asymptote here. And then I would just do the same things that I did the last section, but this is also an asymptote so it doesn't touch, and then look for a vertical and horizontal. But that's what they call an oblique asymptote. And actually, if we do our last the problem we did before, we should be able to have found here an oblique one, because this is also one more out of another. So if you could look here, there's also this slant asymptote that it doesn't hit either. But we were able to graph it without it. But in this one, we want to make sure that when you see that n is 1 bigger than m, that there's a slant asymptote somewhere there. So go ahead and you can graph this to see what it looks like. Or we can do it, since I'm not going to go through the whole problem. We can, this is x squared minus x minus 8 divided by x plus 3. So if you look here, let me zoom out. So you see that, and then this line of y equals x minus 4 right here is a slant asymptote. It's undefined on that line. So go ahead and pause and write this down, and finish it if you can. And then try guided practice number 2B and 4A, guided practice number 2B and 4A, and I will see you in class.